This is up. But yeah, this is Understanding Bitcoin Source 10, where I'm going to talk about forks, and specifically Taproot, because Taproot's kind of interesting and no one really knows what it did. So this is what I will be going into. Anyway, oh, sorry. So let's try and switch it again. There we go. What is Taproot? That's the big question that this is supposed to answer. And Taproot is actually something related to botany, which Roz is an expert. Roz, can you explain the Taproot?
I'll make a song about it.
Huh? You want to give a description of a taproot? Well, it's right here anyway. A large central and dominant root from which other roots sprout laterally. So I guess the idea was you package a whole bunch of changes in Taproot, and Taproot's a backbone of a lot of future things as well. But Taproot, aka SegWit v1, it's a set of changes to Bitcoin's consensus rules, and it's classified as something called a fork. Does anyone know why we'd want to make Bitcoin changeable through forks?
Well, it's software, so isn't that how we upgrade software? Is by merging in a different branch, or is it?
Yeah, that is another usage of the word fork, and I'll go into forking and why it's decided. But in general, to Bitcoin's consensus rules, because a lot of people don't want to have any changes to Bitcoin. We were talking about ossification earlier with Michael Saylor. So yeah, why wouldn't someone or why would somebody want to change Bitcoin? Do you guys know any of the motivations for previous changes?
ZK proofs, any future upgrades?
Yeah, exactly. Yeah, so upgrades for privacy or scaling.
In the past, to address bugs.
Yeah, a lot of big bugs in the past would have lost billions of dollars today. So so those are pretty good reasons. And do you guys know any specific examples of?
There's that inflation bug.
Yeah, there was an inflation bug. That's a specific.
That's a good reason to fork.
Right. Yeah, that is a good reason when you have a bug in consensus.
Yeah.
A big fork was SegWit, right? SegWit v0.
You can use this desk if you want back here. If you want some surface area.
Yeah.
Yeah, use that one or this one. Whatever. Eat.
But yeah, SegWit was a huge fork, and there was a lot of other forks before SegWit that people didn't really go up in arms about.
Make Bitcoin more efficient, or to improve Bitcoin. Is that the catch-all for some of the bit denominated?
Yeah, but the problem is
forks?
improvements change with the individual. It's what is an improvement, what's not. Some people
There's some
want
subjectivity into this idea that it's improving.
Right, exactly. Not everyone wants privacy, for example. They're like, let's stop with all the privacy stuff. Let's make all the amounts public. Some people want, the government to have more control of Bitcoin. Some people don't really care about Bitcoin as a sovereign asset. They just care about an asset that doesn't depreciate as much as the US dollar. So, yeah, I think it's interesting to at least look at the motivations for these forks. But going into what Roz was saying, let's talk about what forks are. So in here, I say in software systems, there's a concept of version control. So if you ever heard anything like Git or SVN, and version control is when you use a program to periodically save all of your code. It's like you're making these checkpoints. And whenever you save a new version of your code, the software gives that version a label. And this label is called commit. And it's actually generated from the changes that you made. It's essentially like this hash. Each commit keeps track of the changes that were made for that saved checkpoint. And when they were made, the author that made them, information initialized on the software setup, and any messages the author would like associated with the change, is put into that commit. So, if you look at the Bitcoin Core code base and you click on commits on GitHub, you'll see all of the authors that made different changes to different checkpoints in the Bitcoin Core code base, with messages that they wanted to add to explain the context.
Can we pull it up, like an example of?
Yes, we can pull it up. Let's open a new window here. So if we look at Bitcoin, GitHub, we'll go here. If you click on commits, 40,000 commits.
Can you make the text a little bigger?
Yeah, 40,000 commits. So a lot of commits.
Or?
Huh?
Since when?
Since ever. Is the idea.
Since
Yeah.
10/31/2008.
Yeah. Since whenever it was entered into source control, at first it was put into something called SourceForge.
Yeah.
And I don't know if you use Git or SVN, which is another version control software.
I think there was a trivia question about version control being introduced to Bitcoin by Sirius, like maybe a year after.
Yeah, because there was releases
Right.
at first, and then eventually they're like, yeah, hey, we gotta make this public and allow people to contribute in open ways. And
Was it not GitHub originally like SourceForge or one of those other?
No. SourceForge still exists today, I think.
But Bitcoin,
too.
the original GitHub wasn't the.
No, yeah,
repo.
I think it was on SourceForge.
It was, yeah.
But yeah, it's something separate from GitHub.
Okay.
And GitHub is kind of the standard today.
But this would cover all of the commits from that. Like when you're looking.
Yeah. As long as it's using Git,
Yeah,
then you could port things over, and even if it's not, maybe there's probably a piece of software that convert your commits from SVN over to GitHub or Git, the protocol. GitHub is a website that uses the Git protocol, but there's other websites that also use it. So Bitbucket, for example, they just offer features on top of Git.
So GitHub is just the most well-known.
Right, but Bitbucket's also used commonly, and so is GitLab, and all these are places where you could set up your repository. And your repository is where all your code goes, and that's where you make your commits, and these websites track them essentially, and have features to allow others to collaborate with you using a nice UI. But yeah, if we look at Bitcoin Core, we could actually see all these commits here. FanQuake, he's a big contributor. You have to actually click on the icons, and you could see, he's spent almost every day, making commits, and specifically to Bitcoin.
Right.
And you have these messages in them, name, messages, when it happened, and if I want to view the details, then I can click here, and it gives me the whole message that he decided to add, along with his change, the title of his change, and then I can see the files that he actually touched. So this is a pretty small change.
And how does that work when they do like a commit or something like because anyone could basically go there and commit something?
No, it's protected by maintainers.
Okay.
Yeah, usually you'd make a fork of Bitcoin, a source code fork,
Yeah.
and then you'd make a change there, and then you'd make a pull request, something called a pull request, which is like a request for change to the Bitcoin core repository.
Uh-huh.
And then people review,
Mhm.
and the only people who can merge are maintainers.
Okay.
And
So that fork, that's like an individual fork just on your machine, that you're running, so that you can make these changes.
Yeah.
And then the pull request is showing the rest of the community, hey, look at these changes I made on my fork. You guys should
Exactly.
adopt my fork.
Yeah. So, and you could also make another branch on the same repository if you have the rights to do that. And then you could say, hey, take this from this specific branch. But, I don't want to get too into the weeds with the version control, but I do mention some more of this stuff here. So I mentioned, what each commit keeps track of. I showed you guys what that looks like. And really, forks are when a developer copies a program's source code and all its previous commit information and develops an alternate version of the code in a different version control repository. So again, this repository is almost imagine like a Word document. And imagine every time you save a document, it makes a commit. And the commit allows you to add, let's say if it allowed you to add extra information, it would be like a version control piece of software where you can go back to every checkpoint that you saved at. So again, these documents are like repositories. And imagine it's like if I copied Prem's file and I made some changes and I said, hey, you want to take this?
Well, I put my essays on GitHub, and then Michael found a typo.
Right.
So, he had forked the essays,
Yeah.
and then he submitted a pull request for the typo correction.
Exactly, yeah. So that's how things get done. And yeah, forks are good and healthy, and it's how people contribute to open source software. But the forks that we have in Bitcoin are a little bit different. So forks in Bitcoin consensus. A fork in Bitcoin typically refers to a source code fork that includes consensus changes. That's typically what people refer to as a fork. So usually these consensus changes recognize the existing history of the blockchain. If you look at something like Bitcoin Cash, how's it going? but they permit new consensus rules in every block going forward. So consensus forks change something consensus, and that is like the new modus operandi for all the nodes that have followed this consensus fork. And sorry, 1 second, just pulling up. So before we were talking about source code forks. Not all source code forks are consensus forks. They are mutually exclusive. And does anyone know why someone would want to make a source code fork of Bitcoin but not consensus fork? There's a specific example maybe that we've looked at before.
Is it like the other nodes, like Knots or one of these other
Perfect,
ones?
yeah,
Okay.
Knots. Yeah, Bitcoin Knots is a repo made by a guy named like Luke Dash Jr. or Dashier, however you want to say his name. And he forked Bitcoin, like only the source code, but had consensus be the same so that you could add new policy rules. So, every node has its mempool, and mempool is a waiting area for transactions. And let's say you wanted to add new rules for how your node accepts transactions. Well, Bitcoin Knots, it allows you to have more rules than you'd be able to choose from Bitcoin Core. And maybe sometimes altered rules, maybe they disallow things as well. But it's essentially if someone wants to change policy and not anything consensus, they can make a source code fork, maintain that, and push it to people to give them more options on how they want to operate their own node in mempool.
So in other words, like your node might be running on different policies, but you will accept any block that match the general consensus though. Like you haven't changed consensus, but your mempool might look different.
Yeah.
If the block is coming in, you're going to accept it even if it has transaction that your node doesn't accept.
Exactly. Yeah. So you'll always accept blocks from other people if you have a source code fork, and your blocks will always be accepted by others, but the transactions in your waiting pool or the mempool don't have to be the same as Bitcoin Core. Yeah, and they cannot move out of consensus because that's not the goal of a lot of these source code forks. Let's see, next slide. So soft forks versus hard forks. Has anyone heard of these terms and know the difference between them?
I feel like soft forks is typically in activation conversations where you're like activating something that was reviewed, or like you kind of soft fork and update the repo, where a hard fork is like contentious. That's the word I always see, contentious hard fork, where somebody just takes it and like adds something, and it's that I don't know if that like, that's just how I think of it. Like hard forks are bad.
Yeah.
I don't think that's true. So why do I think of it like that?
Well, I think of the difference between soft forks and hard forks has to do with like consensus or backwards compatibility.
Yeah.
Oh, okay.
So like a soft fork is backwards compatible, but a hard fork would not be not necessarily maybe necessarily. That's usually the way I think of it.
Is that true?
Yeah.
But the hard fork is gonna split the chain also, no?
Yeah. If
Hard forks lead to a
if you
change,
change
right?
consensus, then the old nodes will no longer respect your new rules in a hard fork, at least.
So outside of Bitcoin and just like pure software development terms, like are
Yeah.
most of
We
the-
don't really use soft
So
and hard
fork,
forks.
soft fork is almost like a Bitcoin.
Yeah, I'd say it's a pretty Bitcoin specific thing.
Interesting.
Does it have anything to do with BIPs being, approved or anything with BIPs?
Yeah, BIPs are when people make the proposals to like fork Bitcoin, whether through soft forks or hard forks.
Either or.
Yeah, exactly. Either or. They're both allowed it in BIPs. People just kind of throw out their ideas and see what can make Bitcoin
So is
better.
backward compatibility the like difference, or how would you?
Yeah, I'd say it's the difference. And I'll go to the next slide so you guys can actually.
All right, here it is.
So yeah.
Maybe went over.
Yeah. Yeah, but I wanted you guys to think and discuss first. But yeah, soft fork, it produces blocks that are always accepted by consensus of previous versions of the software. Changes are implemented in a way such that the old software versions ignore what they don't recognize. So software doesn't reject legacy blocks, even if they include unvalidated transactions. And yeah, basically what that means, if we're looking at something like SegWit only was a soft fork that was contentious in the community for lots of different reasons. But the only way SegWit could work is if you got a majority of nodes to agree to run the software. If they did not, then SegWit would respect the old like legacy rules and kind of discard their own for consensus at least.
Wait, a majority of nodes, not miners?
Yeah, well, miners don't really control what's in your node. So I'm talking about like at an individual level. If I was the only one who was running SegWit, then I would respect all of the old blocks and transactions if they were mined. And all of my stuff would also, they'd get sent to you, but you would recognize it differently from how I want you to recognize it. So SegWit transactions that use like this witness portion, they are anyone can spend transactions to legacy nodes. But if a legacy node got a SegWit transaction and was able to mine it and ended up on the dominant chain, then for consensus to be maintained, the SegWit nodes would have to accept the blocks, even though they don't respect it going forward in their like mempool. So anyway, it was a very tricky chain when you made SegWit because there was a chance that people wouldn't respect the upgrade. If a majority of the network, like miners and nodes, didn't respect the change, then your SegWit locked UTXOs could be spent by anybody.
And so that could theoretically still happen if a majority of the nodes decided to like revert?
Yeah, they could revert as well.
Interesting.
But you know that'd be that would be very bad. You know?
Yeah.
Well, yeah, and I imagine people like anyone who's using SegWit wouldn't revert, right? Because you don't want your stuff to be anyone can spend. Yeah, and then I was talking about these things. End flags manage what's validated when all newest consensus data is present. Yeah, I was talking about what happens when you're validating these scripts and basically you have to detect that there's a witness as part of a transaction. And that's what gets validated. But if an old node was only able to send you, the transaction version that they understood, then there would be no witness to check. Yeah. So going to hard forks, they can produce blocks that aren't accepted by consensus of previous versions of the software. So if we're looking at something like Bitcoin Cash, you can make very large blocks, and these large blocks would not be accepted by the legacy nodes. The legacy nodes could produce blocks that are accepted theoretically by a hard fork, but it just doesn't work the other way around.
So Bitcoin Cash would accept blocks from Bitcoin.
Theoretically, it could. I think they made some changes so that it wouldn't.
Okay.
But yes, theoretically, they could accept blocks from Bitcoin while still maintaining their bigger block limit. Although eventually they'd have to split, right? Because the rules are just not the same.
But the image I had of a fork, hard fork was that you had all these blocks, right? And at some point, you kind of like you have a split.
Yeah.
Where you have like then the Bitcoin Cash and then Bitcoin. How could, if like these two chains are kind of like next to each other,
Yeah.
how could one accept blocks from the other if they're not connecting?
Yeah, I mean, Bitcoin Cash did make some changes so they wouldn't accept the old Bitcoin blocks, but if they wanted to, they yeah, they could, because they could say we accept all the blocks in this other chain, but we also accept these new rules.
Okay.
But if you're trying to do a hard fork, you're not going to have the majority of hash power. So if you were accepting these legacy blocks, then you'd get like beat out pretty quickly. Yeah. So it's best, even as someone who's advocating for a hard fork, if I was, I would program it such that there's a hard cutoff of when I would not accept certain types of blocks that Bitcoin would generate. And I'd make a distinguishing feature in my own blocks for every block. So yeah, Taproot is a soft fork. Yeah, that's this whole slide here. So there's some features added by the Taproot soft fork: Merkleized alternative script trees, Schnorr signatures, public keys as addresses. These are kind of what was featured in the BIP, and these aren't an exhaustive list of changes. These are like the big things. Yeah, these are the big things that are listed in the BIP and that people wanted to focus on. So has anyone heard of any of these and want to take a shot at explaining what they are?
Schnorr signature, so that's
Yeah.
a privacy primitive, like, or what is the?
It's a
Schnorr?
digital signature, yeah, primitive.
Oh, okay.
It's an improvement over something called ECDSA, which is elliptic curve digital signature algorithm. It was, I'll go into it like later, but it is a lot simpler to use than ECDSA. And the only reason it wasn't used in the past was because there was some like legal issues related to copyright or something
So
like that.
that expired, and it was like, okay, now we can.
Yeah.
We can soft fork to get Schnorr, where like it's not like Schnorr was an invention after Bitcoin.
No.
It was there to be utilized in the initial design, but there was a legal reason that Satoshi went with
ECDSA, yeah.
Because when I hear about Taproot, I feel like Schnorr signatures is the thing that is driven home as the motivation. But these other things, Merkleized alternative script trees, and then pub key or public key as addresses, I don't think I really hear anything about these. I feel like it's all Schnorr signature.
Yeah, I mean, Schnorr is a huge part of Taproot. And
What is
it
NAS?
enable, yeah, it,
What is that?
Can I
Uh-huh.
try?
Yeah.
So Merkle trees. Oh man, like there's a bunch of different.
It's a data structure.
Yeah, but like it has what are they called? Like
Leafs?
No,
Yeah.
like it sets requirements for how the output can be spent. But like the Merkle tree is like a bunch of different possibilities, and then it all just gets hashed, right?
yeah, I mean, that's a simple way. But yeah. Yeah, you create a Merkle tree, you put in a whole bunch of, well, in this context at least, a whole bunch of scripts. You create this construction called a Merkle tree, and you can get an output called like a Merkle root, and that commits to all the values that you put in. So it,
So that's where we get the Taproot.
no, it's just part of.
Well,
it's-
why was it called Taproot if it allowed us to create this mass data structure for script trees and have scripts that have that you called it Merkle root?
All Merkle trees have a Merkle root. So Merkle trees, yeah, a data structure. It's used in Bitcoin consensus. So, like for example, when a block has a whole bunch of transactions in it, you actually compute a Merkle root using a Merkle tree of the transactions.
But that's where the idea of Taproot came from.
No.
So why did it get called Taproot if not for the Merkle root?
People made a whole bunch of plant themed things,
Well,
like
Merkle
graph.
root is a root.
graph root.
So where else is the Taproot if not the Merkle?
Well, trees are big in computer science in general,
Yes.
and the root of a tree was already pre-existing.
Right.
Mass was also invented before like the Taproot upgrade was conceived of, like in its modern form.
Okay.
It was an independent proposal.
Okay.
Yeah, Taproot just seems, I don't know the complete reasoning. I'm sure maybe some forum on there explains how they got to
You
it.
couldn't use a pub key as addresses before Taproot?
Technically, you could. Like in the original Bitcoin, they did allow public keys as addresses, but we've moved on from that. And the standard afterwards was having public key hash as your address.
Okay, to the pub key hash.
Yeah. So it wasn't really a standard to put whole public keys into your like script pub key, if you guys remember.
Wait, so when I send like the BC1, that's a hash?
Well, remember I did the address understanding Bitcoin source? And remember there's like an encoding, like the BEC32M?
Mhm.
So it's actually like, it's encoding information, yes, of a hash.
Wait, so is the BC1, is that the address that gets hashed, or that is the hash?
No, well, in Taproot, there is no hash. It's a public key.
Okay.
But yeah, in previous versions, it was the address is an encoding of like your script pub key. And a script pub key includes the hash. It also includes like the version number of SegWit that it's targeting. So yeah. Remember I had the addresses. I know, like maybe I'll do another one of the addresses and the encodings, like BEC32 or base58, the earlier one. Yeah, and then I also wanted to say these improvements require a basic understanding of something called tweaking. So I'll go over, tweaking. It's not about being on drugs or anything. Yeah. So, tweaking. Tweaking is a process where you take a commitment, like the output of running the SHA-256 function, and you use it almost like a private key. So in Schnorr, as well as ECDSA, private keys are like very big numbers, and then you use it to perform we call it multiplication on a point, but multiplication is defined differently. But imagine it like a private key is this value A, and you're multiplying it with a point, multiplying it because it's not defined as the multiplication you might be thinking of by a point called G. And then that gives you the public key. So your private key times this constant point G of this curve creates a public key. And with Schnorr, public keys can be added together to make joint public keys. And the private keys can be summed and used to generate joint signatures. So tweaking is pretty much about taking commitment to some value and trying to use that commitment as a private key, almost generating another public key, and then adding that public key onto some other public key that you're using. I know it's kind of like sounds weird,
So you get
but
more privacy from all this?
yeah, in a way you get more privacy.
More sets of private keys, like extends. With Schnorr, they can be added together to make joint public and private keys. So you have a whole nother from what I understand, that's like extending the possible end of key pairs, right? Or is it?
It definitely is.
So
One of the
there.
I guess I'll go to the next slide. But one of the benefits is you could use the same like public private key pair multiple times, and as long as they have a different script, or if you want to tweak it randomly, you can. And then the output script could not be recognized. Basically, you can make different addresses using the same key pair, which is nice. Yeah, I guess that's the easy
so
way.
every time you're using the same key pair, you have a different pub key.
Yeah, script pub key, or like that locking script that I talk about. So your address ends up becoming different as well. Yeah. Yeah, but I mean, people still don't use a static one. They still do derivations and make child keys. But if you wanted to use a static one, you could have a different address every time if you tweaked it differently.
But if I don't use the same address, how's everybody going to know what digital collectibles I have?
Yeah, yeah, definitely a problem. Yeah. Then I have some code. This is taken from BIP 341, which is like Taproot, and they have reference code on how they do things, and this is like the actual tweaking code. Pretty much what's happening here is tagged hash. You don't actually hash things in a lot of the Taproot applications. Well, you hash them, but before you hash them, you prefix a lot of the things that you hash with tap tweak. And that's done for some other reasons, because you don't want to double up using a hash function. Pretty much they wanted to make a unique hash function for Taproot. And part of doing that is just saying, we're going to modify this function to prefix the message with Taproot specific terms like tap tweak. Let me know if it's not, if it's too over, the head, or yeah. And then what you do here is you use the x coordinate from the public key, which is doesn't matter too much, honestly. And anyway, this is the tweaking. So what you actually tweak, it's not Merkle root. First, you add the Merkle root with the public key, and then you hash that with the scheme, and then you use that t as that private key. So remember I said you multiply it with g, the generator point. Generator point is always static, and when you take a private key, multiply it by g, you get a public key. So then you get a public key from this, you add it onto p, it makes q, and then you basically get to return q. And you can do the same thing for the secret key, or the private key. And if you tweak the private key, you could have a joint private key that could be used to sign things in a way that the joint public key can verify. Anyway, yeah, like I said, not super important that you understand all the details, but I just thought it was interesting to throw in here. So I added the Merkle tree, a diagram maybe to help with visualization. So Merkleized script trees allow transactions to have multiple possibilities of scripts to run. So scripts, they can be very different from each other. I could make a script that says, hey, give me a value that is equal to 1 plus 1. And that's a super easy script, right? And I could say, give me a value that's equal to 2 plus 2, and 3 plus 3, and all these different kinds of scripts. And let's say I want to make a UTXO that says, people can spend any one of these scripts. They can pick one, and then they can fulfill it. Either 1 plus 1, 2 plus 2, or 3 plus 3. And that's what mass allows you to do, essentially. It allows you to hash, or imagine this is a function. You take in a whole bunch of different scripts, and it generates this Merkle root. This Merkle root gets put, just imagine, in your address somehow. And when you're spending from that address, there's a way for you to say, I want to use this script to fulfill the spending condition. Yeah? No? Can that make sense? Okay.
Well, like, could you give like an example, like tangible?
Like yeah, in terms of what, like
for example, like the different type of scripts, like.
Yeah, well, maybe one of my scripts says, like I have a UTXO and it's locked with a script that says it needs Prem and Randy to sign to be spendable.
Yeah.
And then another script path it says me and Roz need to sign off for this UTXO to be spendable.
Okay.
So at the time of spending, what you actually do is you give something called a Merkle proof, which shows that output value right here can be made from some values down here.
Down there.
Yeah.
And how would he kind of like sign it, or like kind of?
Oh, he'd still have to give me a signature,
Okay.
and then I would provide a witness, which is like almost like the unlock script. Well, it technically includes the locking script as well and the unlock script.
The unlock script. Okay.
Yeah, and then I present that with a Merkle proof that shows there is a way to go from data 4 to hash 1, 2, 3, 4.
Okay.
Yeah, I know there's a lot of things, maybe intermediate things to explain as well, but this is like my best effort. But
so like in the example that you gave,
Mhm.
that where one of the datas is you and I have to sign for the transaction, or another piece of data was you and Roz would have to. Like
Yeah.
either one of those two will satisfy and would allow the UTXO to be spendable.
yeah, as long as I declare to my Bitcoin node which path I'm taking by including what we call a Merkle proof, which is like the path from this root all the way, like to data 2 or data 3, then my node will accept it. It'll be like, okay, he committed to this value because this value is part of his address.
Mhm.
So that means at the time of this money being locked, it was all these scripts were possible to be used to spend from. But the cool thing about this is that if I decide, let's say, I have and you can have a whole bunch of different scripts. There's a limit, but it's pretty high up. I forget what the actual number is. But you could have 100 different script paths. So I could say maybe I want to add another one. Like me and David need to sign off, and all I have to do is commit it to an address that I give you. And once you pay money to that address, it now becomes spendable by any of us. And when I want to spend, I declare which script I want to use, and I have to collect, of course, signatures from you guys. And the nice thing about it is, if I use the me and David path, then the Prem and me and Roz and me path, no one has to know about. It's just a nice feature.
So it's only the actual path that was used that gets revealed, and all the other 99 of 100 paths just gone.
Yeah, exactly. No one will ever figure it out unless I tell people. Right? Yeah.
And like a multi-signature wallet,
Uh-huh.
what would be the difference between, because let's say you can do a script and say this hash cannot be spent unless Prem authorizes it.
Mm-hmm.
It makes me think a bit of a signature where two parties need to sign it in order to go through.
Yeah, I mean, there's definitely.
Is there what would be the difference? I'm super far.
Oh well.
There's
yeah. Let's. I'm trying to think of a use case. Yeah, let's say we're So this is a way to make threshold signatures. There's better ways to do it, but one way is, we're a board, right? Let's say we're on the board of some company,
Yeah.
and we wanted an address such that it needs 2 of us to spend from that address.
Yeah.
So what we do is we make this address be consisted of a whole bunch of scripts that are different subsets of like two of us.
Mhm.
So like one's, you know, me and Prem, me and you, and these are all like script possibilities that you could choose from. And then once like we actually want to sign off on like, let's spend this money that was given to the board, the two that want to sign off give their signatures and you reveal that script. But the rest of the possibilities of who's on the board get to stay hidden.
Yes. Okay.
Yeah, which is nice because.
Those are like the smart contracts, right?
Yeah, I'd say scripting. You can make these smartish contracts. Yeah, so there's cool things you could do. Basically, this allows you to hide information that you committed to as part of your address, and that's a nice quality to have. So yeah, and this part you could kind of like ignore. It's kind of what I was saying before. But using this Merkle root of the scripts, you tweak the public key, and then that tweaked public key is what's used as the address.
Yep.
What's going on? And then I had some more here. I know that maybe this is not the best thing, but the most interesting, but I put when spending a script from a leaf, you know, which would be represented as one of these data buckets, a Merkle proof is required to prove the script was committed to in the Merkle root, which I kind of touched on before. But, you know, we'll move past this. The internal public key is the public key that you tweak. So you have a key pair, and then you take this root of this Merkle tree to tweak that public key with to make your address. But again, let's just move on from mass. Yeah, and I was saying, you know, one cool way to spot Taproot changes in the code is you could do things like this: witness version equals, and when you see 1, that means that that's Taproot specific code. There's also like other indicators you can use to see Taproot specific parts of the code, and that was kind of interesting. And there's a lot more to Taproot than what's written in the bit. And I kind of briefly mentioned that, you know, at the end here, one of the end slides. Schnorr signatures. So we kind of touched on this before, but Schnorr signatures are an old signature scheme, you know, like we were discussing. It predates Bitcoin, but because of these legalities, it couldn't be used in Bitcoin itself because it was at the time of release, it was pretty much already all built with ECDSA, which is free to use. And just as a tangent, ECDSA is kind of like a play on just DSA, digital signature algorithm, and DSA is a different algorithm that doesn't use anything elliptic curves, but it was also made to escape copyright of RSA. So RSA was released. You know, people were trying to put copyrights on RSA. They made DSA. Then Schnorr signature was released. People didn't like that. They were trying to find like ways to tweak the protocol to make it free and open to use. And then we got ECDSA. Yeah. So it's simpler to implement than ECDSA. Like, you know, stupidly simpler to implement, and it contains a lot less mathematical complexity, which is nice because you could start like manipulating things, and you could start thinking of new schemes to do. And there's just a mathematical cleanliness to all of the improvements you can make on these signature schemes. So the two things that I mentioned here are easy key aggregation. So there's like a primitive approach of key aggregation, which is just like, which is kind of used in tweaking, which is I have a public key, Prem has a public key, we add it together, and now that public key is needs both of us to sign. But when we sign, there's a way to combine our signatures into one signature. So no one knows that that signature and the public key was 2 people. So you can do that with Schnorr signature is very easy. That's a primitive approach. We just like add our public keys, then we get one public key to represent us both. But there are some security vulnerabilities with doing it that way. So they developed something called Musig. And then they had some improvements on Musig, so they developed Musig 2. But it's essentially all the same. It's a way to aggregate keys together. Another thing, you get small signatures with Schnorr signatures, 65 bytes versus 72 bytes for ECDSA, you know, which is just a nice enhancement. And yeah, I was gonna include some of the like applications of things like Musig, but you get a lot of privacy benefits from Musig, or even like Mast. I was gonna kind of like at least briefly mention the improvements you get with Lightning. So yeah, like So with Taproot, it's kind of interesting that. So let me go back because I did really explain something. You use this Merkle root to tweak the public key, but there's also a way to just provide this Merkle root and a signature with the public key that you tweaked. So the internal public key, that private key could be used to generate a signature that you tweak, and you could just say, hey, this is a signature. I'm not using any of the scripts. So you could give a signature as an alternative to solving one of the scripts that you committed to. And if you don't want any scripts, usually people make a random hash, and then they just tweak it with that to say it's like unspendable, but also for the privacy of no one knows my exact key pair. Oh yeah, and I was gonna say, in Lightning, like there are schemes that you could use to, in the future, use one signature to spend from that like Lightning multisig, right? If you use musig, then like people don't have to know that it's a multisig, which they do when you do it with script. There's like a check multisig command that everyone sees. So when you spend from that Lightning channel, like it's like, oh, that was probably a Lightning channel. We see this 2 of 2 like multisig, and Lightning scripts are actually very distinguishable from just like regular multisigs. But if you were to use something like musig, you start to like include some ambiguity in like what that transaction was. So it gives you some privacy. That's just what I want to cover. So there's some lesser known Taproot additions. There's a lot more than just this, but these are things that some people don't know about. Minimal byte representations for numbers. So one interesting thing about Bitcoin is like before Taproot, I could have a script that says, hey, give me a number that's equal to 1 plus 1, and then you could solve my script with giving me 2 in my transaction. But you don't just have to give me like the smallest 2 you can. You could actually prefix the byte selection with zeros. And the problem with that is you get this, how's it going? You get this thing called like script malleability. Where you could end up with different transactions or with different witnesses for certain inputs that essentially mean the semantic like same thing, and that causes some like issues. Malleability in general, we don't like it. So one thing that Taproot did is it made as part of consensus having the minimal bytes needed to represent numbers when you fulfill a script to eliminate some of the malleability. Even though the witness isn't necessarily included in the transaction hash, it is included in like the witness transaction hash. So less malleability there is always welcome. It also removed the 10,000 byte script limit, which allows more complex applications like BitVM. It also allowed some other things. Does anyone know what the removal of this 10,000 byte script limit in transactions allowed?
Ordinals?
Yeah, exactly. Yeah, exactly. The whole ordinal theory and inscriptions. So before you had this 10,000 byte limit. You could still make inscriptions pre-Taproot, but you're limited by 10,000 bytes. Once this was removed, you're now limited by the maximum size of a transaction. And a lot of people do not like Taproot because of this change. But at the same time, you get a lot of good things from this. Like you can make very complex BitVM applications for anyone who's been following that or interested in that, because you could fit more opcodes. So it could be used, for different things, and it's not all bad. Just because you have inscriptions doesn't mean this removal of the byte limit doesn't yield better things for scaling.
Can you talk about BitVM a bit?
It's like you're making almost like a computer through a series of transactions. Yeah, but the protocol isn't just like one transaction in an arbitrary program. It's like a protocol for defining a program across like multiple different transactions. And you have different roles, like there's a prover, and then there's like a verifier, right? And then what I do is I give you a program as the prover, and then when it's time to fulfill this program, so like let's say I give you a program, and I'm like, hey, I have the answer to this, or I can get the answer to this. And you're like, okay.
Yeah.
And then like later on, I'll go and I'll give you like this thing called the proof that says, hey, like run this on your own like VM almost.
Okay.
And then you run it and you're like, maybe you see that something's wrong with my proof. It's not quite correct. There's a way for you to challenge me on chain after your VM said, hey, this thing's wrong, and actually like catch me in my lie if I couldn't find the answer to the program I gave you. And if you were to catch me in my lie, you get all the money, right? But if I wasn't lying, then like I would end up getting all the money. And that's like the high level of BitVM. Pretty much you're replicating some of the steps of a program that's run by this virtual machine within Bitcoin transactions in the script portion of it. Yeah, the protocol is a little bit like more complex. That's why that's kind of like the high level.
Yeah.
But yeah, I'd give you a program that you could run on some VM. I'd give you some input. You could run it. Hopefully it works. If it doesn't, then you challenge me on chain. And there's a way that you can, again, like force me to either give you the right answer or catch me in my lie and take all the money that we collateralized on Bitcoin.
What would be the goal of lying in this case?
Try to steal.
Yeah, or if I couldn't find the answer, like if I gave you a program and I said I could find the like an input that gets me my money on this wager, and I couldn't find the input, then I might lie to you, right? But once we go on chain, like I can't lie to you. There's a way that you can find around like log n time that I'm lying.
Okay.
So like you could find a pretty efficient way that I'm lying if you worked really hard to.
Interesting.
But Bitcoin doesn't actually work yet, right?
It does.
It does?
Yeah.
Just no one's built anything sufficiently complex with it, right?
Yeah.
It's like, you know, it's like you said, it's building a computer, but when we say that, it's actually building like the gates that create a computer.
Yeah.
Things like that.
But Super Testnet, remember he had his
But that's
simple
not
implementation.
BitVM.
Huh?
Just like
It is, but he doesn't quite implement it like the paper, but like I would say it's close enough that I'd call it one of the first BitVM implementations or the first one. But you've had other people go and implement things in BitVM like Citria. Remember that sidechain we spoke about? They do have a working version of BitVM that is compliant with the paper, and Robin, I'm pretty sure, has actually made implementation as well, because he was talking about having recently, didn't he say something about, was it Blake that he ran or something like that, one of the hash algorithms? But yes, he's starting to actually generate transactions and use BitVM as a protocol to like accomplish things that you can't with regular Bitcoin. Yeah, so there's good progress, which I should have added that to the BitDevs list, and maybe we can, but big improvements are being known there. Yeah, anyway, this is the last slide. It's almost 7, but does anyone have any particular questions or things they want to ask in general?
Whew.
Yeah.
Deep.
Yeah. Maybe I should have broken it down, made it a little bit simpler.
We have some,
Yeah.
we have some commentary. SegWit was a mistake. We should have hard forked to a bigger block size and avoided the current plague of being able to store data at cheaper rates in the SegWit portion of the block than the main 1 megabyte block.
First of all, who said that?
It was not discussed or disclosed to the layman, and in hindsight, it seems absurd that we sacrifice backwards compatibility for giving a discount to where you store transaction information. From Lembo Bomber.
It's just people are so outspoken with their opinions.
Uh-huh.
Let's talk about that during BitDevs.
Yeah. Well, no, I think
so I can really.
everyone's entitled to their opinion. I think it's like at least useful to like look at their perspectives. But you said we sacrifice backwards compatibility. Not really. Again, if the majority of the network did not go with SegWit, then all those SegWit transactions would be anyone can spend. So it very much was a consensus move, and like, yeah, I don't know. To say it's not backward compatible is just like also incorrect. So yeah, I don't know what to say about that. For giving a discount to where, and the goal wasn't to give a discount.
That's the thing.
Yeah, the goal was to decrease certain things like transaction malleability, right? To allow things like the Lightning
Add that
Network
backwards,
to work
just add it.
optimally. Huh? Okay. Discount for SegWit. Yes, there was a discount for SegWit. But you said we sacrifice backward compatibility for giving a discount to where you store transaction information. But
explain the discount a little bit. Like, it's not necessarily a discount just for the sake of a discount and to save you. It's more to incentivize the UTXO set becoming smaller, so that you put together inputs and have hopefully less amount of outputs.
So part of this discount encourages spending or consolidating your UTXOs. So pay to witness public key hash is actually cheaper it might be the same. I think it might be a little cheaper to spend than pay to public key hash. And part of that was about incentive alignment. People want consolidation of UTXOs, having a UTXO bloated. When you have the set bloated, it takes more resources pretty much. So you actually want your UTXO set to be as small as possible, even if you had a bigger blockchain stored in memory, which is kind of what we have right now when you have the witness data that isn't kind of counted towards like a hard block size limit. We changed it to block weight, so you could actually store more data per block, but legacy nodes actually discount. I mean, legacy nodes don't even know about the witness data of transactions. They just see that it was mined. And yeah, it is, yeah, I don't know what else to say about that. Yes, there's a discount. I think the discount was made like with good intentions, and it did incentivize the things that it wanted to incentivize as a protocol, which again, UTXO consolidation, making that process to be a lot easier. And
Will there ever be another discount, or do you think the Pandora's box and sort of the backlash is kind of removed?
I don't know why there would be.
Yeah, there probably wouldn't.
Yeah, I think part of the discount is also to like again incentivize people to move to SegWit, because once you move to SegWit, you reduce transaction malleability, and then you are able to use things like the Lightning Network without this like risk for some things. You know, and transaction malleability is when I'm making a transaction that's supposedly pays you, and I give you the transaction ID, and I'm able to do something such that like I malleate the transaction and get a different transaction ID and give it to a different set of nodes. So a malicious way of taking advantage of that is like Prem's an exchange, and he pays me something, and like I takes his transaction and am able to do something with his signature, which I can't mess with it like arbitrarily completely, but there were certain things I could do with the signature to make it slightly different. And then I'd get a different transaction ID. And if theoretically I was able to get the majority of nodes using my transaction ID, using his signature, then I could say, hey, your transaction never broadcasted. Send me another one. And then he'd send me something twice. This actually happened in one of the exchanges. So it was kind of an issue. But someone kind of played exchanges with that trick. So anyway, malleability is bad in general. You typically want there to be one way to satisfy a transaction, and not malleate the transaction ID and trick Prem into sending me another Bitcoin because I said his transaction ID couldn't be found because I was playing some games.
Did they get away with a bunch of money from the exchange?
Yeah. No, I mean, yeah. Yeah, exchanges are being hijacked like left and right, in the early days. Yeah, even the Silk Road, right? Was it Jimmy Zong or Zhang? I remember with the Cheeto tin box on our trivia.
Jimmy Zhang, yeah.
Yeah. So yeah, even him, right? He hacked that Silk Road. So yeah, it was very easy for them.
Although he didn't see it as an exploit, he reported it. And Ross
no.
said, no, this is how I understand the story, was Jimmy said, like, swept some coins and was happy to return them, and Ross said, no, keep them, and continued to, like, button up.
No, that was not what happened.
No,
Ross messaged him, he's like, hey, I know you've been stealing. Let me know how you've been stealing, and you can keep the coin.
Yeah.
And he says okay, and he let him know, and Ross fixed it. And he said he wouldn't go after Jimmy.
So the idea that he was willing to give it back, you would say that never happened.
No, I don't think he's ever said he would give it back.
I thought that would happen. I thought that he reached out and said, I was able to take this. This is bad, and Ross.
No,
was
I think Ross.
Well, I bet you now he wishes.
I mean, I can verify.
In hindsight, like if he just returned it, the government would have come after him.
I'll verify the story later, but I think Ross figured it out first, and then reached out to him.
Reached out and said.
And then said, hey, tell me, and like I won't like do anything or like ban your account or something. And he told him, and he got to keep the coin.
We have one more comment from our special guest here. I don't know if it's going to play right, but
Our special ed guest?
It's an AI voice. Sorry, I'm gonna.
The final fork in Bitcoin is now perfection. Devs should pack it up. Their work is done. We have the soundest, hardest money. There is now second best.
there is now.
That is.
There is now a second best, I guess.
Yeah, that is not Sailor AI voice. It's
No,
actually
it's
yeah.
Sailor spelled SAILOR.
Right, yeah.
Sailor
Or, yeah, what's the actual voice that you said? It's
Gigaspook.
Gigaspook,
It's the
yes.
Gigaspook play.ht. So
Yeah,
you
so
wanna
it's
use
technically
Gigaspook,
not Sailor, so
it's
no
Gigaspook.
no problems with using it. It's Gigaspook.
But there is now second best.
Yeah.
Gigaspook.
But yeah, I'll end the stream, and we will start transitioning to BitDevs. So
And beverages,
Yeah.
help yourself.
thanks for anyone
Thank
for
you
coming.